We're going to do a probability review. So here we go. Simulation. This is pretty basic. The law of large numbers. If we observe more and more repetitions of any chance process, the proportion of times that a specific outcome occurs approaches a single value, and the probability of any outcome of any chance process is a number between 0 and 1 that describes the proportion of times the outcome will occur in a very long series of repetitions. So what this is saying is basically, so we all know probability is essentially a fraction, right? Or a decimal. It's a number between 0 and 1. And that number describes how many times that outcome should occur out of some total number of outcomes. For example, if I'm going to roll a six-sided die, the probability that I get a 5 would be 1 out of 6 because one of the sides has a 5 on it and there are 6 total sides. The law of large numbers states specifically that if we do this, if we roll the die a lot of times, then the proportion of times we roll a 5 over the total number of rolls should approach 1 out of 6, which is a very long-winded way of saying if you do the thing enough times, then the actual outcomes will match up with its probability. Okay, so what this doesn't mean is that you should expect precisely these results in the short run, right? That's how gambling works, right? Just because the probability of something happening is a certain value doesn't mean you should expect it in a very short period of time. If I roll a die thousands of times, let's say 6,000 times, 1,000 of those times, or around that much, will be it will land on a 5, and the rest of the times it won't. But that doesn't mean exactly 1,000 out of 6,000 times it will land on a 5. That doesn't mean if I roll it 6 times, 1 out of 6 times it will land on a 5. It just means that as you do it, over a long period of time, it approaches that. The other myth, the law of averages, just because, and this sort of piggybacks off of this myth, just because something happened doesn't mean the other thing is going to happen next or makes it more or less likely. Just because I flipped a coin and it landed on heads last time does not mean if I flip it again, it should land on tails because it's supposed to be about half of the time. It's not how it works. It would be nice if that's how it works, but probability is a prediction about the next outcome based on nothing other than the total amount of expected outcomes, right? Previous events don't matter. If I flip a coin and it lands on tails 5 times in a row, then you might think, well, the probability that it lands on heads the next time would be greater, but no, the probability that it lands on heads the next time is still 0.5 or 1/2 or 50%. So there you go. That's that. When you're going to perform a simulation in a question, so if you're going to explain how you're going to do some sort of simulation in your AP test questions, you follow the same 4-step process that you normally do, right? You state what it is that what question you're trying to answer. You plan by describing what it is you're going to do. This is you do the simulation a whole bunch of times, and then using your results, you answer the question that you're interested in. Now, this is a less strict 4-step process than, say, the ones for significance testing or confidence intervals. It's not necessarily the case that, like, in the plan part, we would have to say, oh, well, you have to say the conditions that are met or this and that. There's not really conditions for performing simulation. You come up with a simulation that you think is going to mimic the probabilistic process that you're interested in, and then you do it. But the 4-step process is the 4-step process, right? Everybody knows that at this point. Just a quick example of a simulation, how they work, what you should be trying to do. In this example, there's you know 5 different types of cards. The fan keeps buying the cards until she gets all 5, and it takes her 23 tries. Should she be surprised? The problem is, what is the probability that it would take 23 or more boxes to get a full set of 5 cards if they're all equally likely, right? So the plan then is to represent the 5 cards with 5 different numbers, 1, 2, 3, 4, 5, and just go through the random number generator until we get all 5 digits. And then we make a dot plot of how many times it took us to get all 5 digits. So basically, this person went ahead and did that. They repeated this process until they got all 5. There's one try, it took them 9, so they put a dot right there on the 9. This is another attempt, took them 16 tries, so they put a dot over here at 16. Yada, 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 did this a whole bunch of times, and this was the dot plot that occurred. Now, if you look at this dot plot, you'll notice, so 23 would be about right there, and at no point during the simulation did it take 23 or more attempts to get all 5 cards or get all 5 digits in our simulation. So what that suggests is that, in fact, it is not equally likely for them to get all 5 cards. Some of them may be less likely than others, therefore it may take you longer to get that particular card or more attempts to get that particular card. So that's basically the conclusion. We never had to buy more than 22 boxes after 50 attempts. So to estimate the probability, the NASCAR, blah, blah, blah. So yeah, this fan should be surprised it took her this long because, in our example, it didn't take that long. All right, probability models. What a probability model is basically a description of some chance process that is one part a sample space and one part a probability for each outcome. A sample space of a chance process is all set of possible outcomes. So a sample space for rolling a 6-sided die is, rolling a 1, rolling a 2, rolling a 3, rolling a 4, rolling a 5, rolling a 6. That's the sample space. If we're rolling 2 die, then this is all the possible outcomes here. There are 36 possible outcomes. So this would be the sample space. These 36 outcomes are as equally likely as each other. A probability model allows us to find the probability of any collection of outcomes, which we refer to as an event, right? So an event can be more than one outcome, and that's basically the little difference. It's a subset. So if A is any event, then we write it as the probability of A. Now, an event can be a singular outcome, and because subsets can contain just one object, that is totally possible. So if A is any event, then we write it as the probability of A occurring. For example, if we're rolling a 5 with 2 dice instead of 1 die, like I've been saying, then the probability would be 4 out of 36, because if we look at our sample space, there's 4 different ways we can roll a 5. There's one right there, one right there, one right there, and one right there. And that's all the ways that you can get a 5 by rolling 2 dice. So 4 out of 36. And that's how you'd write the probability. Again, the probability of any event is a number between 0 and 1. All possible outcomes together must have probability whose sum is exactly 1. So for example, if I add up the probability of rolling rolling a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, a 10, 11, and a 12, if I add up all of those probabilities, it will equal 1, because those are all the possible outcomes. It's like 100% of the total outcomes, right? And that's sort of a good check for yourself. If you're doing your probabilities and you add up all your probabilities and you get a number that's greater than 1, then you done messed up. Likewise, if you're doing something and you get probabilities that are negative or less than 0, that's also not a thing. You can't do that. If all possible outcomes in a sample space are equally likely, then the probability of any event can be found as the probability of A, total number of outcomes in the event, divided by total number of outcomes. So, like I said, there are 4 ways we can roll a 5, and there are 36 total ways the dice can land. So our probability is 4 out of 36. That's it, right? And we know this. This isn't groundbreaking stuff here. The probability that an event does not occur is 1 minus that probability, because if all possible outcomes are, will add up to 1, or all possible events, and the probability of the event you're looking for is this number, then 1 minus that number would be the probability of everything else. And we call this the complement. So for example, the probability of rolling a 5 is 4 out of 36. The probability of rolling anything else other than a 5 would be 1 minus 4 over 36, or 32 over 36. There you go. If 2 events have no outcomes in common, then the probability that one or the other occurs is the sum of their individual probabilities. That's the easy version, right? So when the probability math is easy, this is what happens. So for example, the probability of rolling a 5 is 4 out of 36, and the probability of rolling a 2 is 1 out of 36. So the probability of rolling a 5 or a 2 is 4 out of 36 plus 1 out of 36, which adds up to 5 out of 36. And the reason we can do that is because there's no scenario in which we can roll a 2 and a 5 at the same time. Those events are mutually exclusive. They cannot occur at the same time. If it is possible that the events can happen at the same time, then it gets a little more complicated, but we'll get to that in a little bit. And so 2 events, A and B, are what we call mutually exclusive. Another term, disjoint, if they have no outcomes in common, so they can never occur together. So rolling a 2 and rolling a 5 are disjoint events. They are mutually exclusive. They cannot ever happen at the same time, meaning the probability of doing A and B, rolling a 2 and rolling a 5, the probability of that happening at the same time in one roll is 0. Now, that's not to say that you can't go and roll a 2 and then pick the dice up and then roll it again and roll a 5. That's something different. We'll get to that in a little bit. I'm talking specifically about them occurring at the same time. All right? So don't get it twisted. Here's the same thing we just said, just given symbolically. So if you want to take a screenshot or pause the video to see what this is talking about, then feel free. All right, two-way tables and probability. So when two-way tables are a useful tool that we use when we're calculating probabilities. They can display sample spaces pretty easily, but it makes the math pretty easy once you get the hang of them. So here's an example. So in finding probabilities involving 2 events, a two-way table can display the sample space easily. Consider the following. So consider the following example. Choosing a student at random, the probability that the student has pierced ears is a male with pierced ears, and then is a male or has pierced ears. So part A, choosing a student that has pierced ears. So we're not interested in the sex of the student in part A. We're only interested in whether or not the student has pierced ears or not, right? So if they're a student with pierced ears, so we're not even looking at the sex, we're looking at the total number of students. There's 103 students with pierced ears out of 178 total students. So what that means is that we just do 103 out of 178. So the probability would be 103 over 178. Specifically, a male with pierced ears, so part B, a male with pierced ears would be 19 out of 178. You know, this has to fit 2 different criteria. This student is a male and this student has pierced ears. That means that they fit both yes to pierced ears and that they're a male. So it's just this box here out of 178. So for part C, this one looks like it might be easy, but when we examine it a little bit closely, we see that there's something weird going on. There's a little bit of nuance we have to take into consideration. So if they're a male or have pierced ears, you would think that all you would have to do is say, okay, well, I'll add the 103 to the 190 because that's the males and that's the pierced ears. So it would be 103 plus 190 because that's what we said we were supposed to do, add the event. So 103 plus 190 would be 193. So the probability is 193 over 178. Except that's not a thing. So if I add the pierced ears and the males together, I get a number that's bigger than the total number of students, and that doesn't make sense, right? So let's see what's going on. So we can't use the addition rule for mutually exclusive events unless we know for sure that they're mutually exclusive. Essentially, they have no outcomes in common, because what's going to happen is we're going to double count any event that they share. So if two events are mutually exclusive, are not mutually exclusive, then the rule that we use is probability of A or B equals all of the stuff in A plus all of the stuff that's in B, and then we have to subtract all the stuff that's in the middle because, well, we counted it once when it was in A, and we counted it another time when it was in B, so all the stuff that's in the middle, we have to subtract one of the times that we accidentally counted it. So if I do everything in the yellow circle plus everything in the blue circle, then I've accidentally counted everything in the green twice, so I just subtract that part out. So what that means is we get all of the 90 out of 178 for the students that are males, the 103 out of 178 for all the students that have pierced ears, and then we minus the 19, it was 19, right? We subtract the 19 in the middle because we already counted it once, we counted it twice, we don't want to accidentally count it twice, we don't want to go over. And when we do that, we get 174. All right, so for the complement, it's important to note, for this problem specifically, if the complement is equal to 1 minus the probability of the event, which means 1 minus the complement would give us the event that we are interested in, right? This plus this have to add up to 1. So 1 minus either one of these will give us the other. So in this example, if we're looking for a male, any student that is a male or has pierced ears, 1 minus these 4 students here would be that value that we're interested in, because these are the students that we're not trying to find. So there you go. So the complement contains exactly the outcomes that are not in A, no more, no less, and then this would be what that looks like, right? Here's the events in A, and here's the events not in A. That's how we represent that visually. The events A and B are mutually exclusive if they have nothing in common, and this would be how we represent that. 2 circles that just don't touch. The intersection is all the stuff that's in A and B, and then the union is everything together. And this is, make sure you don't accidentally double count this, right? So these would be the visual representations of those. So this is what this looks like after we match everything up, right? So the 71, the event A is all of these students here, right? So there's 90 total students in the yellow circle. Some of them are in the green, some of them aren't in the green. But in total, there's 90. So 71 plus 19 gives us that 90. And then for the pierced ears, there's 103 total students in the circle, 84 plus the 19, right? Now, you may be saying, well, hang on, this doesn't tell us anything about the total number of people without pierced ears or the total number of females, and you would be right. But we weren't interested in that question. We could come up with a Venn diagram that would help us answer that question. Venn diagrams help us specifically answer one question, and they're useful for that, but they don't answer every question that we can have about a two-way table, unfortunately. How we represent that in words: male and pierced ears, That's the middle part. That's the 19. What about if they are a male but they don't have pierced ears? Well, so A intersected with the complement of B, right? So A, I'm in A but I'm not in B. That's this 71. What about I want to see females that don't have pierced ears? Or, I'm sorry, I want to see females that do have pierced ears. So that would be they're inside circle B, but they're not a male. So, you know, just this part here, that would be the 84. And then this last one here, I don't know if you can read that, it's really low on there. I want all the females who do not have pierced ears. That means they're not inside either one of the circles. That would be just these four. And then you have all 178 students represented there. Conditional probabilities. It's not really that tricky. It's just tedious. The probability that one event has happened, given that another event has already known to have happened, is called conditional probability. Basically saying, what is the probability that this happens if this other thing has already happened? So the probability that an event A happens given that B has already happened is using this symbolism here. Probability of A given B. And this is the formula we use to figure it out. So basically, it's the probability of A and B, or the intersection of A and B, divided by the probability of B. Which, again, not really that complicated of a calculation to do. Here's an example. Consider the two-way table. We just looked at an example of two-way tables. Here's another one. Let's define the following events. E is going to be that the grade came from an engineering and physical science course. So the event E is everything in this row. And then L is that the grade is lower than a B, so everything in this column, right? So what we're looking for is what is the probability of E given L, and then what is the probability of L given E? Basically, what is the probability that there was a grade that came from what is the probability that the student was in an engineering and physical science course given that they made less than a B? And then what is the probability that they made less than a B given that they were in an engineering and physical science course? Two different questions, similar ways that you respond to them. So for the first one, E given L, what is the probability that they were in this row given that they were already in this column, right? So these are all the people in this column. The probability that they're an engineering and physical science student is 800 over 3656. That's it, right? Probability that they were an engineering physical science student, given that they made less than a B, is this number divided by this number, because these were all the engineering and physical science students that made below a B, and this is the part we are interested in. You also notice that falls in line with this formula. What is the intersection? It's the intersection of A and B. That would be this column here, and then divided by the probability of B. Well, B in this case is L. They made less than a B, and there you go. The other way around, what is the probability that they made less than a B, given that they were an engineering and science student? So again, if we assume that they were an engineering and physical science class, then we're looking at just this 800 here over that 1600. So 800 over 1600. And again, it follows the same formula. It's the intersection of the row and the column divided by the thing that comes second, which is this part here. And that's it. See? Looks hard. It's not really hard. Multiplication rule. So the probability that events A and B both occur can be found using this formula, the intersection, right? Probability of A times probability of B given A. Now, where B given A is the conditional probability that B occurs given that A has already occurred. Again, it's not as complicated as it sounds. All right, so to help figure out the multiplication rule, tree diagrams can be little extra useful, right? Both in the circumstances where one event does depend on the previous one and in circumstances where it doesn't. Here's an example in which it doesn't, right? So probability of flipping a coin and getting 2 heads in a row. If I toss the coin, there's half the chance, 50% chance it lands on heads. If I toss it again, there's a 50% chance it lands on heads. So 1/2 times 1/2 is 1/4, right? And then you can also do the same thing to get the other 3 possible outcomes, right? Not too complicated. Here's one that's slightly more complicated. Pew Internet and American Life Project finds that 93% of teenagers from 12 to 17 use the internet, and that 55% of them have a posted profile on a social networking site. What percent of teens are online and have posted a social media profile? So again, we'll start off. Well, 93% of the teenagers are online, which means 7% of them are not. If they're online, then we say, okay, well, what is the probability that they're online and have a social media profile? Well, that would be 0.93 times 0.55. 0.93 times 0.55 is 0.5115. There you go. Now, down here, this one looks a little weird because it's like, okay, well, 0.07 of them don't have online or don't use the internet, and then what's the probability that they have a social media profile? Well, if they don't use the internet, they definitely don't have a social media internet profile. So that's why this is 0 and this is 1, right? If they don't use the internet, then they definitely don't have a social media profile, which means the probability that they do would be 0. There you go. That's everything for probability basics. All right, so discrete and continuous random variables. Random variables in general. They're great. Huh. Cheese and rice. All right. A random variable takes numerical values to describe outcomes of some chance process. The probability distribution of a random variable gives its possible values and their probabilities. So as you can see down at the bottom, we have tossing a fair coin 3 times and x being the number of times that heads was landed on. So the probability that heads was landed on no times is 1 out of 8. Probability was landed on once is 1 out of 8, because as you see, there's 3 ways that can happen. Probability that you landed on heads twice is 2 out of 8 because there's, is 3 out of 8 because there's 3 ways that can happen. And then the probability that X lands on heads all 3 times in a row is 1 out of 8 because there's only one way that can happen, or one scenario in which that outcome occurs. A discrete random variable is a fixed set of possible values with gaps in between, like the last example we just saw. So the probability distribution of a discrete random variable lists the values for X and their probabilities. Every probability must be a value between 0 and 1, and just based on the rules for probability that we just learned, the sum of those probabilities must also add up to 1. To find the probabilities of any event, we add up the probabilities of the particular values that make up that event. I mean, we know this, right? So this is sort of based on, all of this is based on the rules that we know from before. If 2 events are mutually exclusive, then we can add them all up. If we want to know the probability that more than one of them occur, this is what I'm recording with. To find the probabilities of any event, we add up the probabilities for that particular thing, and we go from there. This is what we use when our probabilities in our sample space may not be equally likely. It makes it a lot easier if we just write them out, and then we can go from there. But basically, it's a table where you have the values for X on top, and then the probabilities for each of those values on the bottom. It's literally just it, right? To find the mean, I recommend using lists and spreadsheets in the calculator. I've shown you how to do it in class, but I'll do it on this video so you can see it. But if you don't want to do it on the calculator or you're in a hurry, all you have to do is multiply each value times its probability, and then add all of those numbers together, and that will be your mean, your expected value. Hi, how can I help you? And it's denoted with this symbol, and this is the formula for that, right? Expected value for x is the probabilities of each value for x and then multiplied by each of their each of the values, and then added together. Here's an example of that. I don't know what an Apgar score is, but here's a table. If we wanted to find the mean for the random variable x, random variable being the score of a randomly selected newborn kid on a test, because why not start testing them as soon as they're born? All we would do is we would multiply each of these values times its probability, and then add that all together, and that would give us the value. But there's another way to do it as well that may be a little bit easier. So you can input all of your values for x in one column. You can input all your probabilities in another table. I can barely read that. And then once you have them all in, all you gotta do is say, okay, well, I want statistics, specifically statistics calculations. Now, you would think because we have two columns, we want two variable. However, we actually only have variable for this test for newborns. And then what we do is say, okay, well, I have the one variable. Just leave it at one list, right? Here's my list. I called it X. And then here we have what we call the frequency list. The frequency list is how many times each event occurred. Now we're using probabilities to say, well, it occurred this amount of times, but the idea is the same, right? So what this would do is if we were actually collecting data, like if we had a dot plot, we could look at the dot plot and say, okay, well, this score occurred this many times, this score occurred this many times, and so on. This is essentially the same concept, just still written as a decimal instead of total amount. So we're going to use our probabilities as a frequency. And then sure enough, there's the mean. It also gives us our standard deviation, which we'll get to in a second. But so it looks like the mean or the expected value for a score is 8.12. So babies tend to do pretty good on this test for newborn kids. I guess they should. It's designed for newborn kids, so you would think the newborns would do great on it. You and I, maybe not so much, who knows? So the formula for standard deviation or for variance is that, and then to get standard deviation, you just take that and take the square root of it, right? Because standard deviation is this variance, or the square root of variance. Now, you'll notice what's happening in this formula is they've already found the mean. So they've found the expected value. And what they do is they take each value, each x value, and subtract it from the mean, square it, then multiply it by its probability, and then add all those together. So 0 minus the expected value squared times probability, and all that. So you can do that by hand. Also, though, it's given to you here when you do this in the calculator. So if you're ever asked to do that, I would strongly recommend doing it this way. It's possible to do it by hand. It doesn't seem likely that you would be asked to do it by hand on the test at this point this year in 2020. Maybe back in 2021 when we go back to having really long tests, you would have to do it, but I would recommend using the calculator because that's what it's for. But yeah, that's what that means. When you have to interpret it, it means a randomly selected newborn's Apgar score will typically differ from the mean by about 1.4 units, and units is unspecified because the units were unspecified in the question. And that's everything you need to know about discrete random variables. You can use them, if I asked you, okay, what's the probability that a newborn scored lower than the expected value, the expected value is just a little bit greater than 8, so you would add all of the scores that are less than A, that are 8 or below. If I said what's the probability that a newborn scores higher, then you would add all of the values that are above that. If I want to find the probability that it's some or not others or whatever, then you just add the important ones. So discrete random variables are actually super easy when you're trying to find stuff. All you have to do is add up the things that you need and ignore the things that you don't. Continuous random variables are slightly more complicated, but not really. A continuous random variable takes on all values in an interval of numbers. Probability distribution of x is described by a density curve. The probability of any event in the area under the density curve and above the values of x make up that event. Basically what that means, I mean, it's like with normal curves that we learned in Unit 1 and then also in like almost every other unit. Basically we have, I mean, you can think of it like a histogram, right? The probability of getting certain values in a histogram, or from your histogram, is proportional to the volume that bar for that event takes up on your histogram. That's what this is basically saying. Except if it's continuous, then it's not separated out into sections. It could be one point, it could be several points, it could be everything in between. The probability model of a discrete random variable x assigns a probability between 0 and 1 to each possible value of x. A continuous random variable has infinitely many possible values because that's how math works, that's how numbers work, that's sort of the definition of real numbers. And all continuous probability models assign probability to 0 to every individual outcome, and only intervals have positive probabilities. Basically, that's a byproduct of the way this works. If there are infinite possible values and the sum of that infinite amount of values has to add up to 1, then the smaller you get in each of your intervals, then the smaller the probability is going to be. And you can keep getting smaller and smaller and smaller and smaller until eventually you arrive at a singular moment or a singular point on the curve. But by the time you've gotten to that, you've smushed your volume for your probability so tiny that it doesn't actually exist. The probability for that one thing doesn't exist anymore. Maybe another way to think about it is if we're describing the probability as the area underneath a curve, well, a singular point doesn't have an area, it has just a singular line, and the area of a singular line is 0 because it doesn't have an area, right? That's not how area works. In area, you need a length and a width. If you only have a length with no width, then your area is 0. If I'm building a fence and I only build one side of the fence and I don't build a width to it, and I say, well, how much space is enclosed by my fence? You would look at me like none. Your fence doesn't enclose any space. You just built a random fence in the middle of the grass, and there's nothing. It doesn't wrap around anything, you idiot. So that's kind of what this is saying. So if you only have one individual point, then the area underneath it is just a line, and that line doesn't have probability. Here we go. It sounds hard. It's not. Here's an example, right? So the heights of women closely follow a normal distribution with a mean of 64 and a standard deviation, 64 inches and a standard deviation of 2.7 inches. And there's the normal curve for that. It's got a mean of 64, so it's centered around 64, and it's got a standard deviation of 2.7. Choose one woman at random. Choose one woman. Call her height Y. If we repeat a random choice many times, the distribution of values in Y is going to be the same as the normal distribution, which means if we choose someone at random, then the probability distribution of it's a long-winded way. At this point, we hadn't learned about sampling distributions yet, but you remember sampling distributions. If you're sampling from a normal distribution, then your distribution of your samples will also be normal. Blah, 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 blah. Basically, we can expect our results to be normally distributed. So all that to say, what is the probability that the chosen woman is between 68 and 70 inches tall? Notice we didn't say that what is the probability that the woman is 70 inches tall, because that would or 69 inches tall or 68 inches tall, because that would suggest we're looking at exactly 68 inches tall, not 68.001, not 67.98, exactly 68 inches tall. And the probability that someone is exactly 68 inches tall down to, the micrometer, that would be metric. I'm mixing metric and standard. Standard unit measurements are good. Down to the smallest measurement imaginable, the probability that she is exactly 68 inches tall, well, that's next to zero. The probability that someone is exactly that measurement, it's not going to happen, right? So instead, we say, okay, well, what is the probability that they're between this measurement? Like, okay, cool, I can do that. That gives me a lower and an upper bound, if you will. So what we do, if we're doing it by hand, which we're not, then what we do is we find the z-score for the lower and the upper bound. We find the probability for each of those z-scores, and then we subtract those probabilities from one another. Like I said, it's not that fun, but it's not that complicated either. And again, this isn't really something that you would probably have to do on the 2020 test, because they said you can do it without a calculator. But if you're doing it by hand, this is what you would be doing. If the mean is 64, then this is the z-score for 68. This is the z-score for 70. Those are the two. You go to your table, you find probability of getting a z-score that's greater than 2.2. Find the probability of getting a z-score that's greater than 1.48. You're like, okay, well, it's these two numbers subtracted from each other. So there you go. The probability of finding a woman that is between 68 and 70 inches tall is 0.0562. Now, if you're doing it on a calculator, then first we state the distribution and the values of interest. It's normal. So the height y of a randomly chosen young woman has a normal distribution with a mean of 64 inches and a standard deviation of 2.7 inches. That's what this is shorthand for. That's what that says. And we want to find the probability that she is between 68 and 70 inches. And then if we're doing the calculator and we're answering this in an FRQ setting, then we would want to make sure that we type all this, right? Here's how we'd actually do it in the calculator. And again, I've shown you this in the past, but it's been a hot minute, right? So you guessed it, it's a normal CDF because it's normally distributed, as it says in the problem. So granted, you can get there from statistics or probability. This is the name of the class, but this is the name of the unit, so we're going to go here. It doesn't matter either way. But we go to distributions, and we go to normal CDF. Now, we are interested in the woman being between 68 inches and 70 inches tall. The average height was 64 inches, and the standard deviation was 2.7 inches. That's it. Modern technology, man. It's amazing. I'm going to go through this very quickly because we've done transformations a few times. So in chapter 2, we study the effects of linear transformations on the shape, center, and spread of a distribution. If we add to a distribution, then it moves our center. It moves our entire distribution, but mostly it moves the center. But it doesn't change the shape at all. If we multiply, then, so this is in the format y equals a plus bx, right? Where x is the variable, x and y are the variables, and a and b are constants, right? So a would be like your y-intercept, and b would be like your slope. So if we multiply by a constant b, then, or if we divide, right? Because you can do it, you can divide things by numbers as well. You can multiply and divide. essentially, if you multiply, then it's going to multiply your center by that value. It's going to multiply your spread by the absolute value of whatever number that is. So your standard deviation is going to increase or decrease by the absolute value of whatever that is. And we say absolute value because if you multiply by a negative number, it's still going to make it more spread out. It's not going to make it negatively spread out. That's not really a thing. There's no such thing as a negative distance. But it's not going to change the shape. So neither one of these things changes the shape, which is good. That makes it easy. The same is true with random variables and their distributions, right? So if we've got this distribution here compared to this distribution here, this first one represents number of passengers this guy's Jeep tours takes in any given day, and then C is the money that he collects from each passenger. So clearly, what's happening is we've got the probability distribution for the number of passengers, and then it's $150 per passenger. So all that's happening is each X is being multiplied by 150, right? So the distribution doesn't, the shape of the distribution doesn't change, but the center spread, the center moves from 4 to 600. The spread is now a lot more spread out because it was going from 2 to 6, and now it's going from 300 to 900. But the shape didn't change. The shape is generally the same. Just the metrics we use to measure it have changed. If we then subtract a constant out of that, so like he has to spend $100 on gas for each trip, gas and permits, then that subtracts $100 from each of everything. That moves the center, but the spread is still the same. Instead of going from 300 to 900, we go from 200 to 800, so that's still a 600 spread. The center has moved from 600 to 500, so the center has decreased by 100, but everything else is the same. The shape is still the same. So basically, if you are trying to find the new mean, so if I was trying to find the new center, then I would take the old center, multiply it by whatever I'm multiplying by, and then add whatever I'm adding. Basically, whatever you're doing to the distribution, you do to the mean, and that's how you find your new mean. Now for the standard deviation, since the spread is not affected by adding constants and is only affected in a positive way, negativity does not affect standard deviation. Then all you have to do to find the new standard deviation is multiply by whatever the absolute value of your constant is, whatever your constant b is, whatever your slope is, if you will. And that's it. This is a lot of slide to say very little, right? Now, when you combine random variables, you'd think that would be complicated, but it's not. All you have to remember is that when you're adding two random variables, you add their means together. And if you're subtracting, then you subtract their means. And as long as they're independent, you're good, right? We won't get into if they're not. If you're trying to find the spread, then you can add their variances together, but you cannot add standard deviations together. It doesn't work like that, right? You have to add the variance. Now, if you're going to subtract them, if you're going to subtract the random variables, then again, for the new mean, you just subtract the means. But when you're trying to find the new variance, you still add. There's conceptual reasons why you do this, and the short version is that when you're combining two random variables in any way, whether you're adding or subtracting, you're still increasing the amount of variability in the new distribution because it's two distributions being combined, so it's going to be more chaotic, if you will. So there you go. And here's an example for that. If Pete is joining with Aaron, and this is their two models for their two business models. Well, his mean plus her mean would be the new mean, and then this squared plus this squared would be their new variance squared, and they would take the square root of that to get the new standard deviation. Combining normal random variables, well, it's largely the same, right? The same rules apply. Mr. Starnes likes a lot of sugar in his tea. I don't know why. I don't recommend that. It's bad for you. We have a lot of diabetes in this country. Suppose the amount of sugar in a randomly selected packet follows a normal distribution. There's the mean. There's standard deviation. If he selects 4 packets at random, what's the probability his tea will taste right? So, again, average amount of sugar is 2.7 grams. He likes between 8.5 and 9 grams of sugar in his tea. What's the probability? Basically, that if we pick 4 packets of sugar at random, it'll be between 8.5 and 9 grams of sugar. You would think that all we would have to do is add each of these means together and then just say yes or no. But we're asking a probability question. This is the average amount in each packet, and it probably has this much amount, but each of these has its own distribution. So each sugar packet is essentially its own normal distribution. To find the new mean, you would just add each of these together, right? So 2.17 plus 2.17 plus 2.17 plus 2.17 adds up to 8.68, so that's the new mean. The standard deviation, so 0.08 would be the standard deviation for 1. We have to add their variances together, so we'd have to square this and then add that together, 0.16. So the new standard deviation would be 0.16. So that's the mean and the standard deviation that you have to operate from. And then what's the probability that you get something that is between 8.5 and 9 grams? This would be the visual representation for the distribution. But you could also do it the way we did before. Now that you have the new mean and the new standard deviation, here's your lower bound, here's your upper bound. What is the probability that in a distribution that's normal and continuous, guy who likes between 8.5 and 9 grams of sugar in his coffee will have it taste right if the average amount of grams of sugar is 8.68 and the standard deviation is 0.16. Well, there you go. There's the probability, 0.846. And that's how you would do that in the calculator. Now, again, all of this is good and useful, but it does need to be said that it may be unlikely that this appears on this year's test, right? It's not likely that they will make you do a lot of normal CDF type calculations because they have said you don't need a calculator. So the probability that they have you calculate things is low. But just in case, and if you're watching this in the year that's not 2020, and we're not in the middle of a, pandemic lockdown testing environment, this is useful. So there you go.